And McGill University, and it's my great pleasure to be chairing this session today on deep learning and neural models. Our speaker is Maxence Arnaud from the Université de Paris-Sud. He's a PhD student there, and he's going to be talking to us today about updates on equilibrium propagation to match gradients for backpropagation through time. Maxence?
Good morning, everybody. I'm really happy to be here and tell you more about equilibrium propagation, or EQPROP for short. So briefly speaking, equilibrium propagation is an alternative to backpropagation for computing error gradients in a neural network that receives a static input. And the goal of this research is to bring EQPROP one step closer to conventional machine learning. Okay. So backpropagation is for sure the method of choice for training deep neural networks. However, one feature of backprop that makes it biologically implausible is the fact that the weight update it prescribes does not solely depend on the pre- and post-synaptic activity. Namely, it is local, not local. And conversely, contrastive Bayesian learning, which is used to train energy-based models like Boltzmann machines or upfield networks, has a local learning rule. And equilibrium propagation stands in between, because on the one hand, it is reminiscent of backpropagation in the way it computes error gradients, and also it is very similar to contrastive Bayesian learning because it has a local learning rule. Let me now recall the working principles of EQPROP. So let us consider a neural network whose neurons are described by the variable S and the synapses by the variable theta. By definition, the dynamics of S derive from an energy function E that is itself a function of the input of the neurons and of the synapses to be adjusted throughout learning. So this kind of dynamics ensure that the system reaches a steady state that is denoted here S star, that is a minimum of the energy, as you can see on the figure. So we are in a supervised training setting where the goal of learning is, given a static input X clamped to the visible layer, that the resulting steady state of the output layer that we denote here, y at star, is the closest to a given label y. So for this purpose, EQPROP proceeds in two phases. So during the first phase, we simply let the system evolve on its own until it reaches a steady state S star. And very likely at the beginning of learning, y at star is not going to be any close to y, which is the goal of learning, thus creating a prediction error in the output layer. So during the second phase, in order to reduce the prediction error in the output layer, we're going to elastically nudge the output layer towards y, that is, towards decreasing the cost function L, which amounts, as you can see on the figure, to add an elastic contribution to the energy. And consequently, the whole system is going to evolve towards a second steady state that we denote S beta star that better accounts for the good output. And rather intuitively, the learning rule that EQPROP prescribes increases the energy of the first steady state because it gives a wrong output, and decreases the energy of the second steady state because it gives a better output that is closer to y. So what would be the conventional approach to the same problem, that is, from the point of view of standard machine learning? Well, a dynamical system is pretty much an RNN that can be described with discrete time dynamics of this kind, and that can be conventionally unfolded in time like this. And so for training, we will perform a first-forward time phase until we reach time step t, then compute the loss of interest, and then perform backpropagation through time. So as it stands, backpropagation through time doesn't seem to be readily comparable to equilibrium propagation that we have just described. So for the sake of bringing EQPROP closer to conventional machine learning, could we possibly rewrite it so that it better fits into this conventional setting? Well, the answer is yes, and rather simply, by simply taking the continuous time equations of EQPROP, we discretize them with the Euler scheme, and we end up with a new form of discrete time equations. So up until now, it wasn't clear whether equilibrium propagation, which was originally thought to train continuous upfield networks, could be extended to discrete time models of machine learning. So we propose a discrete time version of EQPROP that we're going to show is equivalent to backpropagation through time on RNNs that receive a static input. And we're going to show that it enables to extend ECPROP training to vanilla RNNs that we're going to call prototypical models, that we have called prototypical models in our paper, including convolutional architectures for the first time. All right. So now, from now on, let us now assume discrete time dynamics deriving from a scalar function phi that we call a primitive function. We also superimpose the first phase, backpropagation through time, over this first phase, and the second phase of ECPROP. Well, as you can see, these two computing schemes look very different. What the theorem says is that they are intimately related. So here's the theorem. So what it says heuristically is that provided that the first phase is well converged, the gradients computed by backpropagation through time over this first phase are equal step by step to the temporal updates of the system during the second phase of ECPROP. We call this property the gradient descending updates GDU property. So on the following animation, each temporal update of the system during the second phase of ECPROP is matched in the same color with the corresponding gradient computed by backprop through time. So now we can state more formally this theorem. So if a system, again, has discrete time dynamics deriving from a scalar function phi, and that during the first phase the system reaches a steady state S star and stays at S star for k steps, then for k time steps, the neural updates of the system during the second phase of ECPROP, defined as such, are equal in the limit of the nudging strength beta going to 0 to the negative gradients of the loss with respect to the neural state computed by backprop through time. And provided we define properly the synaptic updates of the system during the second phase of ECPROP, we can extend this theorem at the synaptic level. We can numerically check the GDU property on a system that perfectly fulfills the conditions of the theorem. So first, take such a system, and take an input x that you claim to the visible layer and run the first phase until you reach equilibrium. Then two, compute the gradients provided by backprop through time. So on the following figure, we show these such gradients for a few neurons in different colors in plane lines as a function of time. And to emphasize that backpropagation through time goes backward in time, we've flipped the time axis. Three, perform the second phase of ECPROP and collect the updates of the same neurons in the same color, and we plot them in dotted lines as a function of time. And look, we are happy because we can see that all dashed lines follow the plane lines, hence showing that the GDU property is perfectly satisfied by the system. Well, the GDU property looks interesting, but it can also be useful. Note that theoretically, if a model satisfies the GDU property, then on this model, the learning rule of backpropagation through time should be the same as the learning rule of equilibrium propagation. And so in theory, backpropagation and ECPROP should perform the same on training tasks with this model. And so remember that the goal of our work is to extend ECPROP training to prototypical models of machine learning. So somehow we would like these models to satisfy the property that we have just mentioned. So in particular, we introduce a fully connected model and a convolutional model on this slide. And it turns out this model do not exactly derive from a primitive function, hence the two following questions. Does the GDU property still hold approximately, that is, numerically on this model? And two, if so, can we expect as a consequence, in the light of the theoretical remark we made, that ECPROP and backprop through time perform approximately the same on training tasks with this model? This is now what I'm going to address. So here are the results that we obtained on the convolutional architecture. So again, the dashed lines indicate the updates of the system during the second phase of ECPROP. The plane lines, the gradients computed by backprop through time. Different colors indicate different neurons or different synapses, and what we can see is that for neurons and synapses within the fully connected and within convolutional layers, most of the dashed lines follow the plane lines, hence showing out of sight that the GD property is very well satisfied by the convolutional architecture. Also, as we had expected as a consequence, when training this model with ECPROP and backprop through time on MNIST, we obtained almost the same performance. And by the way, this performance of ECPROP on MNIST is the best ever reported in the ECPROP literature. We also have the same results with the fully connected prototypical models. that these models satisfy the GDU property, and we also have the same consequences in terms of training. More specifically, this table indicates the error rate obtained with ECPROP and backpropagation through time on energy-based models labeled as EB, on prototypical models labeled as P for a different number of hidden layers, 1H, 2H, 3H. And we also include the wall clock time of each training simulation. And what we can see is that in any case, and as we had expected, ECPROP performs as well as backpropagation through time. And also, training prototypical models is 5 to 8 times faster than training energy-based models, which is extremely interesting from a practical point of view. But nevertheless, regardless of the kind of model we want to train, scaling ECPROP to deeper architecture is really hard. So on the following figure, the height of the bars indicates how well the GDU property is satisfied neuron-wise, synapse-wise, for different number of hidden layers for prototypical models on the lower panels and on energy-based models on the upper panels. And what you can see is that the deeper the network, that is going on the right, the higher the bars, hence the less the GDU property is satisfied. Our main hypothesis to account for this is that the deeper the network, the longer it takes to reach equilibrium, then the more the conditions of the theorem are stringent. So here are our take-home messages. Our discrete time version of equilibrium propagation is equivalent to backpropagation through time on RNNs that receive a static input. We have called this property the GDU property, the gradient descending update property, and we have shown that it could empirically help to extend ECPROP training to prototypical models of machine learning, including convolutional architectures for the first time. Nevertheless, in any case, that is for any model, ECPROP is difficult to scale up to deep architectures. So the last point I want to address is that emulating dynamics on the conventional computer can be extremely lengthy, particularly when we want to train deep architectures with ECPROP. So hence the following questions. Why wouldn't we run this dynamics for free on a real physical system? Also, ECPROP has a specially local learning rule, which makes it an excellent candidate for the development of highly energy-efficient learning-capable hardware. So maybe hardware and algorithm co-development is one key direction of future research for equilibrium propagation. Thank you.
Excellent. Thank you very much, Maxence, for a fascinating talk. We now have just a few minutes for questions. Is there anyone who would like to ask a question? If you do want to ask a question, there are 4 microphones set up. Please go and use one of the microphones. Okay, I'm going to ask a quick question then. So, out of curiosity, do you think that it's going to be possible to develop a version of this that doesn't require relaxing to an equilibrium distribution and so could potentially work in much deeper networks?
Well, I think this is possible if you rethink the way you want to encode the error. The thing is that here, in the context of ECPROP, the error is moving out of the equilibrium. So if you encode the error differently, then it can be possible that you don't need to wait for equilibrium. And I mean, I have examples coming to my mind, but maybe it's out of the scope of the questions, and I can develop it at the poster. Yeah.
Sure.
Yeah.
Okay. Is there anyone else who would like to ask a question? Okay, well then, in that case, let's thank Maxence for a great talk. And if we can get the first speaker for the spotlight talks up here, please. Oh, yes. He's coming here.
Everybody presenting a spotlight in this session, just line up here, please.
Yeah, that one.
My name is Aaron. Pleasure to be here. This is at least 100 times more people than the kind of group I'm used to speaking to, but really excited to be here. I'm here representing Applied Brain Research, and we build low-power integrated AI systems focusing on the full stack from software to neuromorphic hardware to algorithms that are dynamical and continuous in time. And today I'll be talking about the Legendre memory unit, or continuous time representation in recurrent neural networks. So this work was a collaboration between ABR and the Center for Theoretical Neuroscience at the University of Waterloo. So this work is really motivated by long short-term memories, which are arguably the most successful kind of recurrent neural network. They've been applied to many real-world problems ranging from image caption generation to music composition and speech recognition. However, when trained via backpropagation through time, they fall apart when tasked with learning temporal dependencies that span thousands of time steps or more, making them very difficult to scale up in practice to leverage long windows of time. So this motivates the LMU, which is a novel type of RNN with a very special kind of weight structure that we mathematically derived from first principles to uniformly maintain a continuous time scale invariant representation. It does so by orthogonally projecting the continuous time sliding window of input history onto a basis of Legendre polynomials. This makes it very resource efficient with respect to the length of the window. Then what we do is we recurrently couple this linear dynamical system with nonlinear units that learn how to compute interesting complicated functions across time while simultaneously determining what should be orthogonalized by this linear dynamical memory. We published this code on GitHub using Keras and TensorFlow, and you can stack this up and train it via backpropagation through time. And if you want, you can even backpropagate through the ODE solver that's discretizing the differential equations. Although we find that by default, you often don't need to do this. What we do is we discretize the differential equations using a ZOH solver, and that turns out to be good enough for a lot of the tasks that we're interested in. So the first task I want to present to you is the Muted Sequential Mis task. This is a somewhat standard now benchmark for RNNs, where you take the pixels of MNIST and you feed them in sequentially, but then you permute them by a fixed permutation matrix to completely distort all temporal structure. And we found that this outperformed all competitors by over a full %, and we're using the same computational amount of computational resources, but we're actually training 38% fewer trainable parameters and training it for 10 times fewer epochs. And it's important to note here, we're only using 256 dimensions to internally represent all of the 784 pixels. So we're not doing anything trivial like remembering all of the pixels in the image. We're actually dynamically compressing it down into the small scale, into this compressed representation. LMUs also outperform LSTMs on a memory capacity benchmark by several orders of magnitude. LSTMs again fall apart for windows of about 1,000 time steps or more, but LMUs have been shown to scale up to input sequences spanning hundreds of millions of time steps. So this example is actually showing a sliding window of half a billion samples, and we're compressing it down into 10,000 dimensions. Stacked layers of LSTMs are also outperformed by equivalently structured LMUs on this chaotic time series prediction benchmark. Although interestingly, if you interleave the two network architectures, then they actually achieve the lowest accuracy, or the best accuracy, the lowest error. We've implemented the LMU as a spiking neural network, and the resulting patterns in spiking activity have been linked to time cells observed in hippocampus, striatum, and medial prefrontal cortex. We've also implemented it on neuromorphic hardware such as Loihi and BrainDrop. These are special purpose chips that can simulate spiking neural networks with extraordinary energy efficiency, thus letting us do everything that we want to do with LSTMs, but in a power efficient edge application. So if you're interested in knowing more about the LMU or the kinds of tools that ABR is building, the kinds of neuromorphic hardware we're designing, please stop by our poster session after the next few talks. Thank you.
Hi, I'm Zhijian Liu from MIT, and I'm going to present point voxel CNN, an efficient model for 3D deep learning. 3D deep learning has been widely used in applications on robots, VR AR headsets, and self-driving cars. As all these devices are constrained by the hardware resources and require low latency, it is of great importance to design efficient models for 3D model. Designing efficient models need to take the hardware into consideration. On the one hand, an efficient model needs to have small memory footprints because the memory operation is more than 20 times slower than the arithmetic operation. On the other hand, an efficient model should also avoid the random memory access as it is much slower than the sequential access. Conventional voxel-based models are not scalable because the memory consumption grows cubically with the resolution. However, low resolution will also introduce significant information loss, which will lead to a dilemma. With a single Titan XP GPU, we can only afford the resolution of 64 by 64 by 64. But in that case, more than 40% of information will be lost. In order to keep more than 90% of information, we need to double the resolution to 128. But in that case, we need at least 7 Titan XP GPU, which is not practically affordable for most users. Another stream of models directly process the point cloud. To apply the convolution, these models need to first curate the neighbors of each point. However, unlike the 2D image pixels, these neighbors do not lie contiguously on the memory, and therefore organizing these neighbors require considerable random memory accesses. Also, as the relative positions of these neighbors are not fixed, these models have to compute the convolution kernel dynamically based on their offsets, which is also very expensive. And after analysis, we found that up to 80% of their runtime is wasted on structuring the sparse data, not on the actual feature extraction. Intuitively, we can capture the overall structure and find details of an object separately. With this specialization in mind, we propose a new primitive called point voxel convolution. Specifically, we have a point-based branch that extracts the fine-grained individual point features to capture the details of an object. Without a convolution, this point-based branch is very efficient. We leave the convolution to the voxel-based branch, where we convolve over the low-resolution voxel grids to extract the coarse-grained neighborhood information. As the voxel resolution is relatively low, the voxel-based branch can also be implemented very fast. In short, PVConv combines the advantage of point-based model, which is the small memory footprint, and the advantage of the voxel-based model, which is the regularity. We visualize the features extracted from the two branches, and interestingly, the voxel-based branch learns to capture the large continuous parts, while the point-based branch captures isolated and discontinuous details, such as the table legs. This phenomenon is well aligned with our design. On 3D part segmentation, our PVCNN achieves a much better accuracy, latency, and accuracy memory trade-off. It is 2.7 times faster and consumes 1.5 times lower memory compared with the state-of-the-art point CNN. It can also achieve real-time performance on lightweight edge devices, including just a nano, which only consumes the energy of a light bulb. On 3D indoor semantic segmentation, the improvement is even more significant. PVCNN++, which is built upon PointNet++, outperforms PointCNN with roughly 7 times speedup. Compared with the previously fastest model, which is the PointNet, our PVCN is roughly 2 times faster, and also it is more accurate. In the first example, we can see that PointNet misclassified the desk as the chair, while our model gives relatively accurate prediction. Finally, on 3D object detection benchmark, our complete PVCNN accelerates F.net++ by 1.5 times, while improving the MAP by up to 3.5%. Here is an example video where the upper and lower image contain the 2D and 3D bounding boxes. Here you can see that our model has already finished while the baseline is still slowly making progress. To sum up, we designed a hardware-efficient model point voxel CNN that makes the points and voxels specialized in their own strength. Our model won the gold medal in this year's LIFT challenge. Please come to our poster at number 112 if you're interested, and our code has also been released on GitHub. You can visit our project page, pvcnn.mit.edu, for more information. Thank you so much.
Hi everyone, I'm Ricky, and I'm here to talk about how to design. I'm here to talk about how to design neural network architectures that allow efficient access to certain differential operators. This is joint work with my supervisor, David Duvenel. Oh, there we go. Okay. So as an example, we can take a look at the divergence operator. Given a function that maps from RD to RD, the divergence is defined as the trace, or the sum of the diagonals of the Jacobian matrix. This operator appears very frequently when dealing with differential equations. It's also useful for finding fixed point problems. It's also used in continuous normalizing flows, which is a type of deep generative model. So the problem is divergence can't be easily computed for general neural networks. The typical framework we use to take gradients is based on the idea of automatic differentiation. And then generally, this can be used to compute vector Jacobian products. But this means in order to construct the full Jacobian, we would need exactly D evaluations because we can only query a single row of the Jacobian at a time. Okay. Even if we were only interested in just the diagonal elements, this would still require the same cost as computing the full Jacobian. So instead, we're going to restrict ourselves to a more structured architectural form that we're calling hollow networks. And to be more concrete, we're going to be interested in dimension-wise derivatives, which are the derivatives from Fi to Xi. Okay. This includes the Jacobian diagonal and also higher order derivatives when k is greater than 1. So the way we built the network is to first create hidden states that don't depend on the ith dimension. So we'll have d of these hidden states. We then concatenate the ith input dimension with the ith hidden states and transform them into the final output. Both of these transformations can be easily parallelized on the GPU. The computation graph is visualized on the right. And note that these edges denote nonlinear transformations. Okay. So designing the network this way lets us easily disconnect all interacting dependencies because they appear only in the hidden states. So to extract dimension-wise derivatives, we simply need to detach or stop the gradient from flowing to those hidden states. And this functionality is supported by PyTorch, TensorFlow, and most other deep learning frameworks. Okay. So that was a very graphical way of describing the procedure. To understand why this works, we can take a look at the full Jacobian df/dx and see how it factorizes into partial derivatives. Okay. So tau here is the final transformation that takes an x and h. It has two diagonal partial derivatives. The Jacobian of h is block hollow, meaning that the elements are on the diagonals are exactly 0. Okay. So simplifying this, we see that we basically represented the full Jacobian as the sum of a diagonal matrix plus a hollow or non-diagonal matrix. Right. The detaching trick mentioned earlier simply removes the hollow part of the Jacobian, so we're left with just the diagonal elements, and this is why we call our architecture a hollow network. Okay. All right, so moving on to some applications. The first is quite general. It has to do with solving root finding problems where you want to find x such that f of x is equal to 0. The simplest way to solve this is using a fixed point iteration, so you basically start from an initial guess and just recursively update x minus f of x until convergence. Now we can speed up this process by left multiplying by the inverse of the Jacobian diagonal. And this will be referred to as the Jacobi-Newton method. Both methods would give the same solution, but Jacobi-Newton typically finds that solution at a faster rate. Now with hollow networks, these two updates have the exact, it's the same asymptotic compute cost. So we apply this to implicit ODE solvers, which basically need to solve a fixed point iteration in an inner loop. And we found that it uses only half as many iterations. We can also apply hollow networks to generative models called continuous normalizing flows. Now, the brief summary is that if we transform samples from a distribution through an ordinary differential equation, we can also track how the probability density function evolves. By using hollow networks, we are able to compute the change in density exactly, and this led to outperforming existing related methods for amortized variational inference. So for our final application, the Fokker-Planck equation describes the evolution, again, of probability density as samples are transformed through a stochastic differential equation. And the way we propose to fit stochastic differential equation models is basically to match the left-hand side and the right-hand side of the Fokker-Planck equation, and we can efficiently compute the right-hand side if we parameterize the appropriate functions using hollow networks. I'm running out of time. The main takeaway is that even though for general neural nets, dimension-wise derivatives are very difficult to extract, we can design architectures that allow efficient access to these derivatives. And we've shown they're quite useful in a lot of different cases. Thank you.
Good morning, all. This work is called Sequential Neural Processes. So let's review some background first. Generative query networks and neural processes are exciting new meta-learning frameworks. These can learn a stochastic process from few context observations that are provided at test time. So for example, in a 3D scene, a context would contain a camera position and the image that would be seen from that camera position. And from the context, an encoder produces a distribution over the representation of the process on which some queries can be asked. And the model then returns a distribution over the outputs that would be expected as a response for that query. So in this work, the question that we ask is, what if these stochastic processes also had some underlying temporal dynamics? Because in these cases, these are clearly static. Some examples of these might be, for example, there might be some 2D canvas with some shapes moving on it. And an agent can maybe only observe a cropped patch from a certain viewpoint. Or it could be a 3D arena where from a given camera viewpoint, you can only see what you can see from that viewpoint. Or it could be like a 1D function that's changing with time based on certain dynamics. So if we try to simply extend the baseline, we could do that by appending time to the query. But our findings show that this does not work that well. The generation quality leaves something to be desired, and it also cannot generalize to long time horizons. So in this work, we propose sequential neural processes. So instead of using a single latent to model the entire process, we use an autoregressive sequence of latent variables, which can be procedurally generated using a transition model. So each ZT acts as a representation of its own time step. And so we can, in principle, at least indefinitely roll out these latents. And in a given episode, the context observations also arrive sequentially. So this can be seen as an agent gathering some observations from the environment. And some time steps can also have an empty context. An interesting perspective on this model is of meta-transfer learning, because we can think of the latent ZT as the hypothesis of the agent of the current environment. So from new observations that it receives at any time step, it does not need to learn everything. It only needs to update the hypothesis from the new observations. To train the model, we use a variational approximation, and we infer the latents autoregressively using an elbow objective. Okay, let's see some demonstrations. So we apply our SNP framework to GQN to implement what we call temporal GQN. And and in this demonstration, this is a demonstration of a moving cube. And in the first 5 time steps, we show some context, and then we allow the model to predict it, assisted only by the sequence of the actions that the cube was given. And we can see that 10th step without the context, it does well, and then it can also do well beyond the training time horizon. This is a demonstration of meta-transfer learning. In the early time steps, we do not reveal a certain face, in this case a yellow face, and we can see that the model samples a color for that face, but then when we reveal it, the model updates its hypothesis while also remembering the faces that it saw before. This is just a comparative comparison between the generation quality between GQN and TGQN, showing that GQN misses out on some finer details of the environment. And in this example of a 2D case, we show some initial context, and then we allow the predictions to diverge. So it diverges from the true, but then we can show the context again, and then the model can resynchronize itself with the environment. This is an example of 1D regression, and in terms of negative log likelihood, our model also does well. Okay, do visit our poster. It's after these sessions. Thank you.
Good morning. I'm Xiaoju from CMU. I'm very glad today to present our work, Deep Equilibrium Models, which is a joint work with Zico Coulter and Vladlen Koten. We have a very ambitious goal in this paper. Specifically, we provide proof on how very deep networks can be replaced without loss of representational capacity by a single layer defined implicitly and modeled using an approach that we call the Deep Equilibrium Model, or DEC. Importantly, we established DEC as a very competitive approach that can achieve results on par with or even better than the state-of-the-art approaches, and yet comes with only constant memory cost. We're going to go ahead and introduce a specific kind of network which will help us with this kind of reduction, which is what we call the weight-tied input-injected network. So weight-tying simply means that the parameters are shared across layers. Meanwhile, you re-inject the transformed input to every level of the network, which can also be considered as a kind of residual connection directly from the input level. Now, you would think that this would be a very restriction on the model, but it actually isn't, at least not fundamentally. So theoretically, we show that any deep network can be represented exactly by a weight-tied input-injected network of equivalent depth. Empirically, the successes of some recent works have shown that weight-type deep networks could actually work just as well, such as TrellisNet and universal transformers. Therefore, an alternative view of deep networks is to think of them as repeated application of some transformation f theta. But in practice, for many types of such models, which are essentially performing the simplest fixed-point iterations, they tend to converge to an equilibrium at its limit. Well, you do need to assume certain level of stability, of course, in the model, but in practice, the layers we designed and used for deep networks usually already assume such amount of stability, or they will quickly blow up anyway after, say, 110 layers. So the goal of our model, the deep equilibrium model, is hopefully clearer by now. We advocate for finding the equilibrium point directly and more quickly by formulating it as a root finding process. So our task, in a certain sense, as deep learning architects is a lot easier now. We only need to define one layer, which is f theta. In the forward pass, we just directly compute the equilibrium point, which essentially solves the root of a nonlinear equation. And in the backward pass, we directly differentiate through this equilibrium point using implicit differentiation regardless of the forward pass trajectory. A few points. Our work actually shares a few similarities with the classical RPP theory as well as the attractor network. However, in DEC, we advocate for explicit replacement of modern structured network with a sense of equilibrium and with proof of its universality. We also demonstrate it as a very practical approach that can even outperform the state-of-the-art models on some very large-scale benchmarks. We also prove that there is no advantage, at least representationally, in stacking DACs. So there's no point in having a term such as a deep DAC. One layer of a very good transformation is literally all you need. In our current formulation for DAC, it's about 1.5 to 2x as slow as the conventional deep networks, primarily because while we're using the faster root finding algorithm, we still aim to find the actual root or approximate it, whereas a typical deep nets with a fixed number of layers are not trained to do so. However, the model is indeed much, much more memory efficient because you only need to maintain the memory equivalent to that of just one layer. We primarily focused on the extension of DAC on sequence modeling, but you can also easily extend the method to instantiate all kinds of DACs. We specifically use two such architectures that have achieved state-of-the-art on various sequence benchmarks. The first one is based on trellis network, which is a kind of temporal convnet that provably generalizes RNNs. And of course, we have a version for transformers, which is a kind of weight-tied multi-head self-attention. And here are some results on one of the large-scale benchmarks where we use the Wikitext 103 corpus for large-scale word-level language modeling. We show a bunch of comparisons for both instantiations of DAC. In all cases, we found that DAC actually outperforms the state-of-the-art approaches with similar number of parameters while reducing the GPU memory needed by up to 90%. This demonstrates DAC as a practical implicit depth model that scales to realistic high-dimensional problems. So to quickly summarize, DAC computes an infinite depth model by root finding while only consuming the memory equivalent to that of just one layer. We believe it introduces an interesting revisit to one of the most fundamental concepts in deep learning, which is essentially what layer or what depth of a model means. If you're interested in DAC and interested in implicit deep learning, feel free to stop by our poster, which is right after this talk. Thank you.
Okay, thank you everyone for coming. Thank you to all our spotlight speakers and Maxence, our oral. That's it for this session. There's now a break. Please, I hope you have a good day for the rest of NeurIPS.